Our entire universe and existence are made up of atoms, tiny building blocks of everything we know. But how did atoms form in the first place? Where did they come from? We understand that atoms are extremely small, but what if the entire universe were somehow a single atom? Picture an atom in your mind, a tiny hub called a nucleus, with super-fast electrons zipping around it. Now, here's a curious thought. How do these electrons keep spinning around the nucleus without slowing down? This question puzzled scientists in the early 20th century and led to the fascinating development of quantum mechanics. Physicists were on a mission to uncover the secrets of atoms. They discovered that each atom has a nucleus, a center with a positive charge and considerable mass, surrounded by tiny electrons with a negative charge. With this basic insight, scientists began crafting a more detailed model of the atom. At first, they imagined it like a miniature solar system, a dense nucleus, like the Sun, with smaller bits. Like planets, orbiting around it. However, this model ran into some big problems. First, when charged particles accelerate, they emit electromagnetic radiation. Since electrons are charged and moving fast in their orbits, according to this model, they should constantly be radiating energy. This would cause them to lose energy, spiral inward, and eventually crash into the nucleus. But we know atoms last much longer than a tiny fraction of a second, so this model didn't hold up. Second, atoms were observed to emit radiation at specific, distinct frequencies, different from the continuous emission expected if electrons followed the solar system model. Quite a puzzle, right? Enter Niels Bohr, a brilliant physicist from Denmark who helped solve this mystery. In 1913, he introduced a groundbreaking idea. Electrons in an atom aren't just randomly spinning around, they are confined to specific, quantized distances from the nucleus. Bohr went even further by proposing that there was a minimum distance an electron could be from the nucleus. It couldn't get any closer than that. Bohr's ideas weren't just guesses. They were built on the earlier work of German physicist Max Planck. About a decade before Bohr's breakthrough, Planck introduced the concept of quantization in the emission of radiation. He suggested that objects could only absorb or release radiation in fixed amounts, not in any arbitrary value. These fixed amounts were defined by a constant known as Planck's constant. Bohr took inspiration from Planck's work and applied it specifically to electrons orbiting the nucleus. He asserted that the smallest orbit an electron would have an angular momentum equal to exactly 1 Planck constant. Larger orbits could have angular momentum equal to 2 or 3 times the Planck constant, but never fractions like 1.3 or 2.6. Bohr's model laid the foundation for a more accurate understanding of atomic structure and helped explain the behavior of electrons within atoms. To fully understand why electrons follow specific orbits and occupy well-defined energy levels, quantum mechanics had to be fully developed. Electrons, like other particles of matter, exhibit dual characteristics, behaving both as particles and as waves. While we might imagine an electron as a tiny planet circling a nucleus, another way to think about it is as a wave that surrounds the nucleus. When waves are confined to a specific space, they must follow special rules. They can't have just any wavelength. They must fit specific standing wave patterns that perfectly match the space they occupy. Think of it like playing a musical instrument. When you fasten the ends of a guitar string, only certain lengths produce distinct notes. Similarly, the electron wave encircling a nucleus must fit within the given space, and the nearest orbit corresponds to the first standing wave of that electron. As quantum mechanics advanced, this model was refined, but the fundamental concept remained the same. An electron cannot approach the nucleus beyond a certain point due to quantum mechanical restrictions that prevent it from occupying a smaller space. This analogy, comparing electron behavior to musical harmonies, offers a bridge to understanding the fascinating interplay between quantum mechanics and the dynamic dance of particles in the microscopic realm. Another way to look at this doesn't involve quantum mechanics at all, but rather focuses on the different energies involved. An electron orbiting a nucleus feels an electric pull drawing it towards the nucleus, while its kinetic energy pushes it away. For a stable atom, these forces are balanced. The total energy of an electron in orbit, its kinetic and potential energy combined, is negative, meaning energy must be added to the atom to remove the electron, much like how energy is required to remove a planet from the solar system. Imagine an electron falling toward the nucleus due to the electric charge, but because of quantum mechanics, it never reaches the nucleus and stays in orbit. This balance of forces allows the atom to remain stable and hold its components together. Now, let's explore the fascinating journey of the formation of the first atom, a process intricately woven into the fabric of our vast universe. Everything around us, from the smallest speck to the largest celestial bodies, is composed of an astonishing multitude of atoms, surpassing 10 quadrillion vigintillion in the observable cosmos. These atoms, the building blocks of matter, are made up of electrons, protons, and neutrons, which themselves consist of even smaller particles called quarks. The origins of these particles trace back to a monumental event known as the Big Bang. The Big Bang theory serves as our cosmic guide, explaining the creation of the universe. This theory suggests that a massive amount of energy was condensed at the birth of the universe, leading to the formation of atoms. However, this is only the beginning of the scientific story. The intricacies of the Big Bang require a deeper exploration of the early universe. Unfortunately, the exact moment of the universe's beginning remains a mystery, leaving us to wonder whether it truly had a beginning at all. Our most reliable tool for understanding the cosmos, the Standard Model of Cosmology, allows us to trace time back to a moment near the universe's inception, where the theory predicts a singularity, a point of infinite density where all matter and energy were compressed into an incredibly small space. However, many physicists are skeptical about the exact accuracy of this prediction. Our scientific journey takes us back to a time very close to the universe's birth. Beyond this point, our understanding becomes clouded with uncertainty. Before this brief moment, the details of the universe's creation remain hidden, leaving us to wonder about the secrets of this primordial epoch. As we continue our quest for understanding, we approach the very edge of time. Yet, the elusive moment when time truly began remains a mystery, inviting further exploration and reflection. To delve deeper into the universe's early stages, we must explore a quantum theory of gravity, a merging of the principles that govern both massive objects and the smallest particles. This cosmic exploration takes place during a period known as the Planck epoch, where the universe's fundamental forces, electromagnetism, the weak force, the strong force, and gravity, are thought to have unified into a single force. Now, let's journey through the timeline of the Big Bang theory. We start before the Planck epoch, entering the era of cosmic evolution. However, to avoid the mysterious singularity at the very beginning, we must tread carefully, acknowledging the uncertainty of the universe's state during this enigmatic period. Our theoretical journey continues with the epoch of inflation. During this time, the universe underwent an extraordinary expansion, far beyond our usual understanding. This expansion happened faster than light, transforming the universe from a tiny point into something much larger. It's important to note that while information cannot travel faster than light, cosmic inflation involves the expansion of space itself, allowing distant points in space to move apart faster than light can travel between them. While inflation offers a fascinating glimpse into the universe's early story, our most significant understanding comes from the phase that followed inflation. Here, we witness the Big Bang not as a single point, but as a period when the early universe was filled with extreme heat, density, and rapid expansion. As we explore this cosmic timeline, we uncover the complexities of the universe's beginnings, exploring the forces and processes that shaped the cosmos. Inflation remains a key theory in understanding this period, though the energy behind this rapid expansion is still unknown. This phase of inflation also erases any information about what existed before it, leaving us with an open question about the true origins of the universe. The Standard Model of Cosmology becomes clearer after the universe's initial stages, as these energy levels can be recreated in modern particle accelerators. However, events during the earliest moments remain speculative, including when the fundamental forces of gravity, the strong force, and the combined electromagnetic and weak forces, the electroweak force, were unified. The origin of the first massless elementary particles presents a cosmic enigma, with several potential narratives. One possibility is that these particles were born in the energetic chaos of the Big Bang, while another hypothesis suggests they emerged from a transformation within the inflation field, where the inflaton field transitioned into the elementary particles that make up our universe today. This pivotal moment in the universe's history occurred shortly after the Big Bang, when the cosmic forces of electricity and the weak force began to separate. Around this time, the Higgs field acquired a potential that granted mass to elementary particles, setting the stage for the eventual formation of atoms. As the universe continues to expand and cool, the once intense heat prevents quarks from forming larger composite particles like protons and neutrons. However, as temperatures decline to around 1 trillion Kelvin, a cosmic transformation occurs. Quarks begin to merge into a hadron gas, producing protons, neutrons, and certain mesons. These mesons then decay into photons and electrons. With each drop in temperature, a process of particle-antiparticle annihilation takes place, producing pairs like neutrinos and photons. Interestingly, a small asymmetry in this cosmic dance allows some quarks and electrons to persist, creating the protons, neutrons, and electrons essential for atom formation. Around 1 second after the Big Bang, during the lepton epoch, the temperatures fall to approximately 5 billion Kelvin. During this time, leptons undergo similar annihilation processes, leaving behind photons and neutrinos. Due to the imbalance between matter and antimatter, a small amount of protons, neutrons, and electrons remain, forming the basic building blocks of atoms. A few minutes into the universe's existence, the era of Big Bang nucleosynthesis, BBN, begins. This period sees the creation of protons and neutrons in roughly equal numbers. However, as the temperature continues to cool, neutrons decay into protons via beta decay. Despite this, some free neutrons combine with other hadrons to form larger atomic nuclei before decaying. This process results in a universe composed of about 75% hydrogen nuclei, 25% helium for nuclei, with trace amounts of deuterium, helium-3, and tiny traces of lithium-9 nuclei. A significant chapter in this cosmic story is the photon epoch, which lasts for approximately 380,000 years. During this time, the universe consists mostly of ionized nuclei, lacking electrons to form stable, neutral atoms. However, during this epoch, the universe remains engulfed in intense heat, causing electrons to become temporary companions to nucleons before the relentless force of their high energy propels them into separation. This persistent separation perpetuates a cosmic cloudiness, where photons, bearers of light, engage in continuous interactions with nucleons and electrons, slowing their celestial journey through the vast cosmic expanse. As the cosmic drama unfolds, the photon epoch continues until the universe undergoes a transformative cooling, reaching a temperature of 3000 Kelvin. At this cosmic juncture, electrons, now with diminished energy, succumb to the electromagnetic force, forging enduring bonds with nucleons in a process known as recombination. This cosmic alchemy marks the birth of stable neutral atoms, freeing photons from their entanglement amid the cosmic turmoil of positive nucleons and negative electrons. Henceforth, these photons embark on an unbridled journey through the cosmic canvas. For cosmic spectators in the cosmic theater, this luminal journey offers a visual spectacle in the present day. The first light of the universe, known as the cosmic microwave background, CMB, unfolds in all directions. This luminous emissary captures the moment when the first stable neutral atoms make their cosmic debut, revealing crucial insights about the early universe and the intricate formation of atoms. As we explore these cosmic revelations, an intriguing question arises: do atoms ever truly touch each other? This question delves into the fundamental nature of atomic interactions, inviting us to contemplate the profound mysteries that govern the behavior of these elemental building blocks. In the grand tapestry of the cosmos, atoms are constantly engaged in a dance of interaction. However, understanding the complexity of these interactions requires us to redefine our concept of interaction. Our conventional understanding of interaction stems from the observable world around us. For instance, when you push a magnet toward another magnet, you observe an interaction as they come close. Similarly, when you bring two differently charged balloons, one positively charged and the other negatively charged, near each other, there's an interaction between their charged surfaces. In these cases, the magnetic or electrostatic forces between the objects demonstrate interaction between distinct entities. The properties of the magnet's poles or the charge on the balloons influence the nature of their interaction, creating a dynamic exchange. At the microscopic level, however, our conventional understanding encounters challenges, leading to a certain bewilderment regarding atomic-scale interactions. If we could zoom in on the atomic level, we would witness a bustling scene where atoms and molecules are in perpetual motion, colliding, twisting, and spinning in a chaotic symphony. Amid this microscopic tumult, a significant revelation emerges: atoms lack distinct boundaries. At the nucleus's core, protons and neutrons cluster together, while electrons exist in a cloud of probability, indicating potential locations they might occupy. Quantum mechanics allows us to calculate these probabilities, revealing that they extend across vast expanses. Yet, in most observable scenarios, electrons tend to remain close to the nucleus. Therefore, unless we're engaged in high-energy experiments, delving too deeply into these intricacies isn't a pressing concern. Since atoms don't have solid surfaces, there's no physical touch in the traditional sense, as surfaces never directly meet. However, touch can also imply a close and influential interaction, and in that sense, atoms are always in contact. Atoms interact because of the electromagnetic force arising from the electric charges of electrons and protons within them. Technically, this force has an infinite range but only becomes significant when atoms are close enough. Sometimes, atoms repel each other due to the electromagnetic force between their electrons. In such moments, it's hard to describe their interaction as anything but touching. Even if it's not instantaneous, it still counts as touching. For example, when we observe a cup resting on a table, at the atomic level, the electrons on the cup's outer edge are repelled by the electrons on the table's outer edge. Despite the gap between the layers of electrons, the atoms are close enough to significantly affect each other. This is evident from the fact that the cup doesn't fall through the table, as the electromagnetic forces between the atoms counteract gravity's pull on the cup. On a large scale, when we say two objects are touching, it reflects the same interaction. On a small scale, atoms can interact in various ways, and it's not as simple as always being repelled by the electromagnetic force. When atoms approach each other, there's a force called the van der Waals force, a component of the electromagnetic force. Surprisingly, this force can create bonds between atoms, leading to the formation of molecules. In a molecule, the atoms are essentially in contact with each other. Interestingly, even the nuclei within atoms have the potential to touch, although this is challenging due to the strong electromagnetic repulsion between the positively charged protons in each nucleus. In such cases, quantum mechanics plays a role. If two atoms are brought close and held together for a certain period, there's a chance, albeit randomly, that their nuclei can mix. This process, known as nuclear fusion, involves two separate atoms merging into a single, larger atom. When the atoms involved are lighter than iron, this fusion releases energy, a fundamental process that powers stars, including our Sun. Now, let's explore the concept of identical atoms within the same element. No two atoms of the same chemical element are truly identical. Firstly, electrons in an atom can exist in different states, meaning two atoms of the same element can differ if their electrons are in different states. For instance, one copper atom with an excited electron and another copper atom with all electrons in the ground state are distinct. The excited copper atom will emit light when the electron returns to the ground state, while the copper atom in the ground state will not. The way an atom forms chemical bonds depends on the states of its electrons. So two atoms of the same element can react differently if they are in different states. Chemists understand this well, and to accurately describe and predict a reaction, it's necessary to specify the ionization and excitation states of the electrons in the atoms. Moreover, when left undisturbed, an atom typically does not possess an equal number of protons and electrons. Even when two atoms of the same element have their electrons in identical states, they are not truly identical. Factors such as their movement or rotation at different speeds can influence their ability to form chemical bonds. Atoms with slower movement, like those in solid tin, have sufficient time to establish stable bonds. Conversely, atoms with higher speeds, such as those in liquid tin, struggle to form stable bonds. Consequently, a slowly moving tin atom exhibits different behavior compared to a rapidly moving tin atom. Now, consider a scenario where two atoms of the same element, with their electrons in the same states, moving and spinning at the same speed, would they be indistinguishable? The answer is no. Like electrons, the neutrons and protons within the nucleus can exist in various excited states. Additionally, the nucleus as a whole can rotate and vibrate at different speeds. Therefore, even if all other aspects are identical, two gold atoms might have their nuclei in different excited states, leading them to behave differently in nuclear reactions. In essence, achieving perfect identicality between two atoms of the same kind is an exceedingly challenging task. Even when dealing with two atoms that are essentially the same chemically and exhibit identical chemical reactions, they cannot be deemed completely identical. This assertion extends beyond considerations of electrons to encompass the nucleus of an atom. The nucleus is composed of tightly bound neutrons and protons, and it's essential to recognize that atoms of the same type may possess a different number of neutrons and still belong to the same atomic species. These variants, known as isotopes, have implications, particularly in nuclear reactions and more specifically in processes like radioactive decay. While the involvement of a particular isotope does not impact an atom's chemical reactions, it significantly influences the atom's behavior in nuclear reactions. Various isotopes have different rates of decay and exhibit distinct characteristics in radioactive processes. The prevalence and significance of nuclear reactions, such as decay, vary among isotopes. Some isotopes decay rapidly, transforming into other elements while emitting radiation, while others remain stable. In contexts like carbon dating, it becomes crucial to differentiate between isotopes of the same element. For instance, a carbon-12 atom is not equivalent to a carbon-14 atom. Simply counting the total number of carbon atoms in a sample does not provide information about the sample's age. Instead, a comprehensive analysis involves counting the number of different isotopes of carbon present in the sample. However, it's important to understand that atoms don't have individual identities beyond what has been mentioned here. If two carbon atoms are in the exact same molecular, atomic, electronic, and nuclear states, then those two carbon atoms are identical, regardless of their origin or past history. Atoms, being the basic building blocks of reality, might also have a color, right? Or do they? When you group many atoms together, you get the screen you are currently looking at, which definitely has color. So, does that mean each individual atom has its own color too? If so, is it the nucleus or maybe the electrons that are colored? And if so, which color? The colors you see are created by the human brain. They don't really exist outside of your visual perception. So what exactly is color? To understand that, you need to grasp the nature of light. Light consists of particles called photons. However, this behavior is only noticeable when observed, otherwise, they act as electromagnetic waves. This phenomenon is known as the wave-particle duality concept, and yes, it is strange. These waves have specific frequencies and are classified into 7 primary wavelength sections, ranging from radio waves as big as Earth to gamma rays as small as atoms. The human eye can only perceive this small section known as visible light, while everything else remains invisible. You might wonder why this particular region is important. It's because the first eyes evolved while organisms lived in underwater environments, and this part of light is transparent in water. Infrared and ultraviolet light, on the other hand, make water somewhat opaque. If the first organisms evolved in sulfur lakes on a planet orbiting a neutron star, their eyes might have adapted to see something like X-rays. Now that it's clear how light forms and how it helps us see color, let's delve into it. In the core of the Sun, hydrogen nuclei undergo nuclear fusion due to immense pressure, transforming into alpha particles and emitting gamma radiation. This radiation bounces around the Sun, colliding with other hydrogen atoms over thousands of years, losing energy in the process until it eventually emerges as visible or ultraviolet light, which then reaches Earth. Light behaves in 2 ways when it encounters a material. It can either be absorbed or reflected. This depends on what the material is made of. Take a blue piece of fabric, for instance. It looks blue because it reflects the blue part of light while absorbing all the other parts. So it's every color except blue because blue gets reflected and not absorbed. That's why things that are black get really hot in the sun. They absorb all the light and don't reflect much. On the flip side, white things reflect most of the light and don't absorb much. All of this is called bulk reflection and absorption. When a beam of light meets a bunch of atoms at the same time, factors like how far apart the molecules are or how they're arranged can affect the colors of the reflected light. For example, even though snow and ice are made of the same kind of molecules, they're arranged differently, making snow white and ice transparent. Meanwhile, water doesn't absorb much light, allowing most of it to pass through. To avoid sunlight, you'd need to dive deep into the ocean. Let's reconsider our initial question: can atoms themselves have colors? In the context of bulk reflection, the simple answer is no. This is because the wavelengths of light are much larger than the size of a single atom, making it impossible to discern colors at such a small scale. However, when we consider thermal radiation, an interesting phenomenon occurs. When a substance is heated, the atoms within it become more agitated, leading to the release of photons. Surprisingly, the emitted light follows the same color spectrum, regardless of the substance being heated. It's important to note that this colorful display only occurs when there is a congregation of particles. Individual atoms in isolation do not exhibit any discernible color through thermal radiation. Now, let's focus on gas discharge. When electricity passes through a group of atoms, it excites them, causing the release of photons. The emitted light appears in various colors depending on the specific substance involved, creating a unique emission spectrum for each element. For instance, hydrogen atoms emit distinct colors, a characteristic shared by elements like iron. Essentially, each element has its own unique color fingerprint, defined by its emission spectrum. While one might think of this as the color of the element, from our everyday perspective, atoms are much smaller than the wavelength of light. Therefore, the concept of color doesn't apply at the atomic level in our conventional understanding. Now, let's address a new question. Why don't protons within the nucleus repel each other? In nature, there are 4 fundamental forces: gravity, the weak force, electromagnetism, and the strong force. While we're familiar with gravity on a larger scale, at the quantum level, the other 3 forces become more significant. Electromagnetism, which is about 10 to the power of 37 times stronger than gravity, is responsible for attracting electrons to protons in atoms. You might wonder why multiple protons in atomic nuclei don't strongly repel each other due to electromagnetism. According to Coulomb's law, in a helium atom, 2 protons should experience a repulsive force that would cause them to fly apart instantly. However, protons stick together because of an even stronger force called the strong nuclear force, which is about 100 times stronger than electromagnetism. This force operates at the scale of atomic nuclei and, although it works differently from electromagnetism, it is the key reason protons stay bound within the nucleus. This strong nuclear force is crucial to understanding why atomic nuclei remain intact despite the repulsive forces between protons. The world of quantum chromodynamics explains how protons and neutrons stick tightly inside atomic nuclei, resisting the strong push from electromagnetism. The strong nuclear force, responsible for holding atomic nuclei together, makes up about 99% of the mass of everyday objects, which might be surprising since people often think the Higgs field contributes more. To delve into the intricacies of the strong force, let's explore the composition of protons and neutrons. Within these subatomic particles, we encounter quarks, tiny entities that make up matter, and gluons, particles responsible for carrying the force. A proton is composed of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The gluons, which maintain the proximity of quarks, possess a color charge, a term distinct from optical colors, coming in red, green, and blue. These colors combine to create the neutral color of white. To achieve neutral charges, one can either blend the 3 colors or use color-anticolor charges. The connection between gluons and quarks plays a crucial role in binding them together. It's noteworthy that only quarks and gluons are affected by the strong force, with gluons functioning as messengers, similar to photons in electromagnetism. When quarks try to move too far apart, a metaphorical rubber band comes into play. Instead of allowing the quark to escape, the required energy gives rise to a new quark-antiquark pair known as a meson. This stipulation ensures that free quarks cannot exist independently, they are always tethered to at least one other quark. The role of mesons is pivotal in understanding how protons and neutrons interact within the atomic nucleus. Despite being weaker than the force acting within nucleons, the strong nuclear force substantially surpasses the repulsion arising from the positively charged protons due to electromagnetism. The intrigue of the strong nuclear force lies in its operation at remarkably short distances, roughly equivalent to the diameter of a proton. However, its potency diminishes rapidly with increasing distance. This characteristic is significant as it imposes a constraint on the size of stable atomic nuclei, preventing them from expanding beyond a certain threshold. To delve deeper into its role, the strong nuclear force, facilitated by mesons, plays a pivotal role in tightly binding protons and neutrons within atomic nuclei. This force works harmoniously with the strong force responsible for holding quarks together within nucleons. Understanding the intricacies of the strong force is crucial for unraveling the nature of matter and comprehending the existence of the objects and life forms we are familiar with. Now, let's explore the size of a proton, a fundamental particle in the subatomic landscape. While one might assume that our understanding of atomic properties, including proton size, has reached a satisfactory level after extensive study, a groundbreaking experiment in 2010 introduced a significant twist. This experiment challenged our existing notions by providing a markedly different measurement for the size of a proton, prompting a re-examination of our understanding. After nearly a decade of careful scrutiny and analysis, scientists believe they have addressed this intriguing puzzle, often referred to as the proton radius mystery. Before delving into the intricacies of the latest discoveries, it's crucial to dispel some oversimplified notions about atoms. Contrary to the idea of a proton being a smooth billiard ball, it is more accurately described as a cloud of quarks held together by gluons, adding a layer of complexity to our understanding of these fundamental particles. Quarks play a crucial role in shaping the proton's characteristics, particularly its positive charge. Understanding the dimensions of this positive charge boundary essentially provides insights into the size of the proton. For several decades, scientists have employed 2 distinct approaches to determine the radius of the proton's boundary, engaging in intricate investigations to unravel the mysteries of these subatomic particles. The first method involves directing electrons at atoms, frequently focusing on hydrogen due to its simplicity, a lone proton in the nucleus orbited by a single electron. Through careful observation of the interactions between electrons and the nucleus, scientists discern where the proton's positive charge begins to diminish, effectively marking the boundary of its size. The second method delves into the energy dynamics within an atom, specifically by measuring the energy required to excite an electron from one state to another. Hydrogen serves as a common subject for this study, with its electron not merely orbiting the proton in a lower energy state but occasionally spending time within the proton itself. The intricate dance between the negatively charged electron and the positively charged proton affects their electrical attraction, influencing the energy needed for the electron to transition to a higher energy level. Consequently, a larger proton is theorized to allow more time for an electron to reside within it, resulting in a weaker atomic binding. In the annals of scientific exploration, the determination of the proton size has undergone a fascinating evolution. Traditionally, researchers reached a consensus using electrons, estimating the proton's radius at around 0.876 femtometers, fm. However, a seismic shift occurred in the scientific landscape roughly a decade ago when a new approach emerged. Departing from the conventional use of electrons, scientists embarked on an innovative trajectory by employing muons in high-energy experiments, casting fresh light on the investigation into the proton's dimensions. This intriguing departure prompted a re-evaluation of our comprehension of proton size, reigniting the quest for precision within the captivating domain of particle physics. Muons, akin to their electron counterparts in many aspects, diverge significantly due to their mass, which is 207 times greater than that of electrons. This unique characteristic results in muons spending a more substantial amount of time within the proton. The heightened mass and prolonged interaction time make muons millions of times more sensitive to the proton size compared to regular electrons in hydrogen. In a groundbreaking experiment involving muonic hydrogen, scientists uncovered a proton size approximately 4% smaller than the previously accepted value derived from conventional electron-based experiments. This captivating anomaly prompted a reassessment of prior measurements, casting a spotlight on tantalizing questions about potential new physics or undiscovered elementary particles. The exploration of proton size has thus evolved into a dynamic journey, challenging and expanding our understanding of the fundamental building blocks of the universe. In September 2019, researchers at York University in Toronto conducted an experiment using standard electronic hydrogen, employing an advanced measuring technique known as frequency offset separated oscillatory fields. By exciting the electron into a higher energy state, they obtained results aligning with the muonic hydrogen experiment conducted in 2010, indicating a proton radius of around 0.833 fm. This convergence of results from different methodologies provided a more cohesive understanding of the proton size, suggesting that the previous discrepancy was likely a result of measurement errors rather than heralding new realms in particle physics. When contemplating the seemingly contradictory nature of atoms, where the majority of space is considered empty, a macroscopic analogy proves illuminating. Envision a table magnified to 1 billion times its size, rendering its atoms comparable to melons. Despite this significant scale, the nucleus at the atom's center remains minuscule and invisible, as do the electrons in their orbital dance. The question arises, why don't objects simply pass through this apparent emptiness, and why isn't light able to permeate these atomic gaps? To unravel the mystery behind the solidity of objects, especially the tactile experience of touching a table, it is essential to delve into the intricate behavior of electrons within atoms. Our initial understanding of electrons might be oversimplified. Unlike the analogy of planetary orbits, electrons do not orbit the nucleus like planets around the Sun. Instead, picture electrons as a dynamic swarm, akin to the swift and unpredictable movements of bees or birds. While tracking individual motions within this swarm is practically impossible due to their rapid pace, their collective behavior forms distinct patterns resembling a synchronized dance. This electron dance is far from arbitrary, it adheres to specific predetermined patterns, comparable to steps in ballroom dancing, governed by Erwin Schrödinger's mathematical equations. These electron patterns shape the character of their movements. The patterns themselves exhibit a spectrum of dynamics. Some are graceful and gradual, resembling a waltz, while others are spirited and rapid, reminiscent of a Charleston dance. Each electron strictly adheres to its unique pattern, and the exclusion principle ensures that no two electrons within an atom perform the same step. By envisioning electrons as participants in a complex dance, we gain insight into the organized chaos at the atomic level, contributing to the overall understanding of the physical properties that define the solidity of everyday objects. While electrons don't tire, transitions between dance patterns involve the exchange of energy. Elevating to a faster dance pattern requires energy input, while moving to a slower pattern results in energy release, often in the form of light. When external energy in the form of light interacts with electrons, they absorb some energy, transitioning to a higher, more energetic dance pattern. For a light beam attempting to traverse through a material like a table, the electrons in the atoms constituting the material eagerly absorb energy from the light, hindering its progress. After a brief interval, these electrons release the gained energy, potentially as light again. The interplay of absorbed and reflected light, coupled with changes in dance patterns, manifests as reflections and colors. This intricate process collectively contributes to the perception of a table as a solid object. Yet, this prompts the question, if light doesn't penetrate far into the table, how does the table feel solid to the touch? The sensation of solidity when touching an object like a table is intricately tied to the dynamic interactions of electrons within atoms. As you extend your hand to touch the table, the electrons in the atoms of your fingers come into proximity with the electrons in the atoms of the table. When the electrons of one atom approach the nucleus of another atom, the established dance patterns of their movements undergo a transformation. This transformation arises because an electron in a lower energy level around one nucleus cannot replicate the same dance around the other nucleus, as that particular slot is already occupied by one of its own electrons. Consequently, the incoming electron must transition into an unoccupied, more energetic role. This shift in dance patterns demands energy, and unlike the absorption of light, this time it is supplied by the force from your probing finger. Pushing two atoms into close proximity necessitates energy, as all their electrons must transition into unoccupied, high-energy states. Attempting to bring together all the atoms in the table and those in your finger requires a considerable amount of energy, more than what your muscles can readily provide. The resistance you feel while pushing against the table with your finger is a result of this energy demand, explaining why and how the table imparts a solid feel to your touch. Now, delving into the question of why atoms form molecules, it's essential to recognize that the visible universe primarily consists of fewer than 100 naturally occurring elements. However, the remarkable diversity of chemical substances we observe in the cosmos and within living organisms arises from the fact that atoms seldom exist in isolation. Instead, they avidly engage in chemical bonding, combining with other atoms to form molecules. This propensity for bonding gives rise to an extensive array of chemical combinations and materials, contributing not only to the myriad phenomena observed in the universe but also to the intricate structures essential for life, energy sources, consciousness, and various macro-scale processes. In essence, the universe avoids monotony because atoms form bonds, resulting in complex chemicals with properties that are fundamentally distinct from their individual constituent atoms. This fascinating occurrence unfolds due to the pivotal role that energy plays in the intricate process of molecule formation, a phenomenon deeply rooted in the principles of quantum mechanics. In the realm of essential chemicals that shape our everyday experiences, such as the air we breathe, molecules take precedence over individual atoms. For example, oxygen presents itself as O2, featuring two oxygen atoms bound together. Similarly, nitrogen manifests as N2, and water adopts the composition H2O, comprising two hydrogen atoms and one oxygen atom. The prevalent existence of atoms in the form of molecules can be attributed to their innate inclination to assume a state of lowest energy, akin to a marble atop a hill that effortlessly rolls down to the bottom. Across the natural world, systems consistently strive to minimize their potential energy, elucidating phenomena like the unidirectional flow of rivers from elevated terrain to lower ground. Energy, a key player in the orchestration of molecular structures, becomes particularly significant when examining the simplest atom, hydrogen, comprising one proton and one electron. Hydrogen typically manifests as H2 or hydrogen gas. Quantum mechanics provides valuable insights into the rationale behind atoms forming molecules as they seek lower energy states. The introduction of a second hydrogen atom brings forth intriguing interactions. As these atoms draw closer, the negatively charged electrons, while repelling each other due to their shared charge, are simultaneously influenced by the positive charge emanating from the protons in the neighboring atom, resulting in an attractive force. A delicate equilibrium is established, marked by an optimal distance where protons prefer to reside, allowing for the sharing of electrons while minimizing repulsion. It's crucial to recognize that the attraction between atoms isn't solely dictated by the repulsion within their electron clouds. Rather, a multitude of intricate interactions comes into play, shaping the dynamic landscape of molecular formation. In essence, the dance of electrons and the interplay of charges at the quantum level pave the way for the cohesive existence of atoms as molecules, each striving for a harmonious balance of energy states. The intricate dance of atoms shaping the formation of molecules is intricately governed by the overarching concept of total energy within a system. This all-encompassing energy factor intricately guides the bonding interactions between atoms, orchestrating the emergence of cohesive molecular structures. Delving into the exploration of the lowest energy state in a two-atom system, exemplified by the formation of a hydrogen molecule, entails a comprehensive consideration of various elements. The kinetic energy inherent in each atom, intertwined with the potential energy dynamics between protons and electrons, contributes to the system's total energy framework. In the realm of quantum mechanics, these complex energy calculations are encapsulated in the Hamiltonian, a fundamental representation of the system's energy. However, unraveling this energy tapestry involves the intricate solving of the time-independent Schrödinger equation, with the Hamiltonian as its guiding force. While this equation poses a formidable challenge to direct resolution, its essence is often graphically portrayed, providing a visual narrative of energy fluctuations as two atoms draw closer. Within this graphical representation, a distinctive dip emerges, symbolizing the system's lowest energy state when the atoms attain an optimal proximity. The optimal state encapsulates a harmonious union where the two atoms in this configuration find themselves in a more contented state at a lower energy level than when existing in isolation. This phenomenon elucidates the natural tendency of hydrogen atoms to synergize, forming molecules of H2 rather than persisting in a solitary state. This electron-sharing pact between atoms, known as a covalent bond, extends its reach to forge similar covalent bonds between a myriad of other atoms. Unraveling the secrets of atomic stability involves exploring the arrangement of electrons within their orbital shells encircling the nucleus. Particularly stable configurations emerge when atoms possess specific electron counts, such as 2, 10, 18, 36, 54, or 86. These magic numbers align with the electron tally of naturally occurring noble gases, which are characterized by chemical inertness and a reluctance to readily bond with other atoms. In essence, the stability and bonding tendencies of atoms unfold a captivating narrative intricately woven into the fabric of quantum mechanics. Atoms embark on a quest for stability, aspiring to achieve a complete valence shell of electrons. This pursuit manifests through either the collaborative endeavor of sharing electrons in covalent bonds or the transformative act of transferring electrons in ionic bonds. The magnetic interplay between the attractive force driving electron sharing to attain a full valence shell encounters a delicate equilibrium with the repulsive forces emanating from electron clouds and protons within the atomic nucleus. Delving into the rationale behind the intriguing magical numbers guiding atomic stability unveils a narrative rooted in the realms of quantum mechanics. Specifically, the Schrödinger equation and the Pauli exclusion principle contribute significantly to deciphering the underlying order. The Pauli exclusion principle asserts that no two fermions, such as electrons, can occupy identical quantum states, necessitating opposite spins for electrons sharing the same orbital. The combination of these principles leads to the identification of specific numerical sequences, known as magic numbers, which dictate the configurations resulting in the lowest potential energy within chemical systems. Navigating the complexities of multi-atom systems, like water, H2O, requires comprehensive calculations. The Morse potential equation, often employed as an approximation, proves instrumental in determining bond lengths that are conducive to the molecule's lowest potential energy. Quantum mechanics, with its intricate principles and mathematical formulations, emerges as the guiding light illuminating the intricacies of nature's behavior. However, it's crucial to note that while quantum mechanics offers profound insights into the mechanics of the natural world, it doesn't inherently provide a deep understanding of the fundamental why behind the nature of existence. Transitioning to the intriguing realm of neutron stars, a compelling inquiry surfaces: is a neutron star akin to a colossal atom? Neutron stars are some of the most extraordinary entities in the vast expanse of the universe. They manifest as colossal atomic nuclei, boasting diameters that extend over several kilometers and possessing mind-boggling density and inherent violence. The sheer existence of such a phenomenon prompts a profound question: how can something of this nature possibly exist? The life of a star is a delicate balance between the relentless force of gravity and the counteracting radiation pressure generated by the fusion reactions occurring at its core. Deep within a star's core, hydrogen undergoes fusion, transforming into helium. As time progresses, the hydrogen supply dwindles, and if the star is sufficiently massive, helium begins its fusion journey, eventually transforming into carbon. In the evolutionary process of these massive stars, their cores undergo successive layering, with progressively heavier atomic nuclei accumulating at the core. Carbon fusion initiates a cascade, leading to the formation of neon, which further evolves into oxygen and silicon. The fusion journey culminates in the creation of iron, an element incapable of undergoing further fusion. Upon the cessation of the fusion process, the radiation pressure rapidly declines, disrupting the star's equilibrium. If the core mass exceeds approximately 1.4 times that of the Sun, solar masses, a catastrophic collapse ensues. The outer layers of the core accelerate at velocities up to 70,000 kilometers per second, collapsing toward the star's center. At this critical juncture, only the fundamental forces within an atom come into play, working to counteract the gravitational collapse. However, due to the effect of the weak force in this hot, dense plasma, newly formed protons can easily change identity to become neutrons, and vice versa. As the temperature drops even further, when the universe is approaching 1 second old, this particular quirk of the weak force becomes ineffective, and the protons and neutrons eventually slow their switching. During this so-called freeze-out, the hadrons choose an identity once and for all. It is during this period that the seemingly arbitrary, fine-tuned constants of nature, in this case, the masses of up and down quarks, have their first real opportunity to shape the future of our cosmos. Down quarks are heavier than their up counterparts, and since neutrons contain 2 down quarks, the mass of a neutron is slightly greater than that of the 2 up quark-containing proton. As the final identity switches occur in an ever-cooling cosmos, the downhill energy slope from the heavy neutron to the lighter proton is favored over the energy-intensive hull in the opposite direction. This slight mass difference ultimately results in an imbalance in the number of protons to neutrons in the universe, with roughly 7 protons to every neutron. This ratio, as it turns out, plays a crucial role in the formation of the universe as we understand it. Protons serve as the foundation for hydrogen and helium, the fuel for stars and the essential components for all other heavier elements in the universe. The prevalence of these charged particles over the uncharged neutrons is what enables elemental interactions, paving the way for chemistry and biology. If the initial conditions were different, if the down quark had been assigned a slightly lower mass during the fine-tuning of our reality, the universe we observe today would be markedly different. If neutrons weighed less than protons, they would have been favored during freeze-out, with more uncharged neutrons than protons. The possibilities for chemistry would be limited. Hydrogen, consisting of only a proton with no neutrons, wouldn't be stable for extended periods. Some of the heavier protons could have been preserved by binding to neutrons before decaying away, forming helium atoms. However, helium is often considered the most inert of all elements. It is inherently stable and reluctant to react. With an excess of generally unreactive neutrons, it would be challenging to envision how nuclear fusion could function in such a universe. We would be left with a cold, dark expanse devoid of stars, galaxies, planets, and most certainly, life as we know it. Therefore, we can express gratitude for the universe's unexplained preference for protons over neutrons. However, this is not the only asymmetry that becomes embedded in the cosmos during this stage of its evolution. Another mysterious yet fortunate imbalance is the absence of antimatter. In the future, as we gaze into the sky, we might catch a glimpse of an alien civilization self-destructing. Though not as visually striking as the explosion of a massive star, it would signify the release of energy from a weapon capable of leveling an entire world. Throughout Earth's history, conflicts, territorial disputes, and discord have been common among civilizations, and there's no reason to believe this wouldn't be the case elsewhere in the galaxy. On a belligerent alien planet similar to Earth, the pursuit of dominance leads to an arms race, from primitive weapons to advanced technologies like nanomachines and atomic bombs. Seeking even more potent sources of energy, these extraterrestrials, more technologically advanced than humanity, harness the power of antimatter. They learn to produce and isolate antimatter particles, suspending them in a vacuum using electromagnetic forces until the moment of deployment. Unlike conventional weapons, antimatter requires no substantial fuel or triggers. Upon contact with the prevailing normal matter on their home world, antimatter particles would annihilate, releasing immense energy and destroying themselves in the process. Just 1 gram of antimatter has the potential to unleash as much energy as a traditional nuclear weapon using around 90 kilograms of fuel. The ongoing arms race on this alien world leads to the accumulation of stockpiles of antimatter weaponry. Whether triggered by anger, confusion, or a simple accident, the detonation of this antimatter arsenal is catastrophic. Day turns into night in an instant, scorching winds lay waste to entire cities, eradicating both warring factions and all other life on the planet. The entire world undergoes a transformation that echoes for centuries. This illustrates the devastating consequences when antimatter comes into contact with matter. Yet astonishingly, we are surrounded by antimatter every day. Now, let's embark on a cosmic thought experiment. What if the entire universe resembled an atom? The observable universe, vast and challenging to comprehend, may, according to certain theories, be relatively insignificant. Current calculations suggest that the unobservable universe could surpass even the immense size of 20 trillion light-years in diameter. Despite its colossal scale, a substantial portion of this cosmic expanse might be devoid of matter, akin to the sparsity observed in the observable universe. Matter, the building block of everything we know, is composed of countless atoms too small to be directly observed by our most advanced microscopes. Scientific evidence supports the existence of atoms composed of subatomic particles like protons, neutrons, electrons, and quarks. Intriguingly, there are theories suggesting a grander reality where everything, humans, the entire observable and unobservable universe, resembles an atom in a larger cosmic context. One such concept is the one-electron universe theory, which proposes that our perception of multiple electrons might actually originate from a single particle moving rapidly back and forth in time, creating the illusion of multiplicity. While this idea lacks robust scientific support, it serves as a thought-provoking starting point for other concepts with more scientific backing. A more widely acknowledged variation is rooted in the multiverse theory, which posits that every atom, electron, and property of matter in our universe could be equivalent to an atom in a grander cosmic scheme. This notion expands our understanding of the universe's intricacies, inviting us to contemplate the vast possibilities that lie beyond the boundaries of our observable cosmos. The idea that our universe could be a mere speck in a broader realm has long intrigued the realms of science fiction. In these imaginative scenarios, our universe might be viewed as a tiny entity on a higher plane of existence, or each atom within us could potentially harbor entire other realities. Infinity becomes a crucial element in these concepts, suggesting that no matter how vast our universe appears, the multiverse theory postulates the existence of potentially infinitely larger universes. From the perspective of these hypothetical vast realms, our universe could seem as minuscule as subatomic particles appear to us. When we observe the universe, we witness the intricate dance of minuscule subatomic particles coming together to form progressively larger structures, from celestial bodies to intricate living organisms. This prompts a profound question: could the universe itself be just a component of something even more grandiose? The merging of the microscopic and macroscopic realms urges us to withhold judgment until we develop a comprehensive theory of everything that seamlessly unifies the principles of quantum and classical physics. According to the prevailing theory on the universe's origin, it began as an infinitely dense singularity before expanding through the monumental event known as the Big Bang. This implies that everything we currently comprehend was once unimaginably small. However, it's crucial to distinguish this initial singularity from an actual atom, as it contained the fundamental components necessary for the formation of atoms. While these concepts may challenge our conventional understanding of reality, they serve as valuable thought experiments, encouraging us to contemplate our place in the vast cosmic tapestry. Although they might be mind-bending, they don't diminish the wonder and significance of our existence. One leading contender for a comprehensive theory of everything is string theory, which seeks to unravel the true scale of reality. In this theoretical framework, atoms are not envisioned as spherical objects but rather as string-like structures that vibrate, giving rise to all interactions in the universe, including the fundamental laws of physics, gravity, and quantum mechanics. However, string theory grapples with challenges, particularly in addressing dark energy, a substantial constituent of the universe that remains a puzzle yet to be fully unraveled. Many string theory models face significant challenges in explaining the prevalence of dark energy when compared to observable matter. In recent efforts to reconcile these disparities, researchers from Uppsala University in Sweden have proposed a variation within string theory. This novel perspective suggests that our universe might reside on the periphery of a perpetually expanding bubble, where everything familiar to us constitutes a small segment of a much larger cosmic structure. Within this bubble, and possibly extending beyond its limits, uncharted dimensions could exist, and the infiltration of dark energy from the broader bubble universe offers a potential explanation. If this unconventional portrayal of reality were accurate, it would revolutionize our current scientific understanding, positioning human beings as infinitesimally small components within a vastly intricate and incomprehensible structure. Nevertheless, it's crucial to acknowledge that this concept serves as a thought experiment, a captivating way to contemplate our role in the vast cosmic expanse. Even if our perspective proves limited and our understanding imperfect, the potential insignificance from an alternate viewpoint doesn't necessarily diminish the intrinsic value of our existence. Now, let's ponder a timeless question: what happens to your atoms after you die? Throughout human history, over 100 billion individuals have departed this life. Considering the law of conservation of matter, which posits that matter cannot be created or destroyed, one might wonder about the fate of these countless atoms. Surely, their atoms must still persist in some form, right? Let's explore an intriguing idea: that the atoms of your departed loved ones haven't simply vanished, but have, in fact, become an integral part of you, the world around us, and are presently embarking on a captivating journey across the universe. Let's delve into how this transformation occurs. The human body is a complex composition, consisting of approximately 60% water, 20% fat, 15% proteins, 2% carbohydrates, 2% salts and minerals, along with 1% other elements like oxygen gases and vitamins. Most of the molecules within our bodies take the form of water, H2O. When an individual passes away, this water undergoes a transformative process. It either evaporates from the body into the atmosphere or seeps into the ground. The speed of this process depends on various factors, including temperature and environmental conditions. Even if the water remains in liquid form, it eventually becomes part of Earth's water cycle, transitioning from liquid to vapor, ascending to the clouds, and eventually returning as rainwater. A significant portion of this rainwater finds its way into rivers and lakes and becomes part of our drinking water. Your body utilizes this water for various purposes, such as integrating it into cells, regulating temperature, and sustaining different bodily functions. Some of the rainwater is absorbed by plants, playing a crucial role in photosynthesis, a chemical reaction involving water, carbon dioxide, and sunlight, which produces carbohydrates and oxygen. The oxygen released by plants is then inhaled by you and other living beings to support life. Moreover, the carbohydrates resulting from water and photosynthesis become an essential part of your diet, as well as the diet of other animals through the consumption of fruits and vegetables. This intricate cycle demonstrates how the atoms that once constituted your departed loved ones continue to contribute to the vibrant tapestry of life, highlighting the interconnectedness of all living things and the perpetual journey of atoms through various forms and functions. As we explore the journey of atoms and molecules further, let's delve into the fascinating realm of metabolism. When you consume carbohydrates from plants, an essential process occurs, the production of substances vital for plant life, namely carbon dioxide and water. This sets in motion a continuous cycle where the very elements you generate contribute to the growth and sustenance of plant life. Now that we've uncovered the fate of water molecules, H2O, in your body, let's unravel the destiny of your soft tissues, composed of carbohydrates, fats, and proteins. These crucial tissues undergo metabolism with the assistance of an astonishing 100 trillion bacteria residing in your body. These bacteria have been constant companions, primarily in your gut, throughout your life. Normally, your body's robust immune system keeps these countless bacteria in check. However, upon death, the immune system ceases to function, presenting these bacteria with the opportunity to consume the tissues within your body. In this intriguing process, as these bacteria metabolize your soft tissues, they use them for energy and reproduction. Picture it as a gradual burn where the molecules digested by the bacteria ultimately transform into water and carbon dioxide, the same molecules formed through the process of burning. Furthermore, proteins in your body give rise to other gases like nitrogen oxides and ammonia during this metabolic process. What makes this process even more remarkable is that these gases, especially nitrogen oxides, are potent greenhouse gases. Nitrogen oxides, for instance, are approximately 300 times more potent than carbon dioxide in contributing to the greenhouse effect in the atmosphere. This emphasizes the intricate interplay of chemical processes within the body, showcasing how, even after death, the elements within our bodies continue to participate in complex cycles with broader implications for the environment. As we delve deeper into the fascinating realm of post-mortem processes, the journey of atoms within our body takes a unique turn. As the initial bacteria continue their metabolic activities and oxygen becomes scarce, a new set of bacteria known as anaerobic bacteria seize the opportunity. Unlike their aerobic counterparts, these bacteria don't rely on oxygen for metabolism. Instead, they produce byproducts such as methane, hydrogen sulfide, and ammonia during the metabolization of tissues. These byproducts are notorious for their unpleasant odors and interestingly serve as potent greenhouse gases. Gradually, these substances exit the body and disperse into the atmosphere. So when you step outside and detect an unusual scent in the air, there's a chance that you might be inhaling atoms originating from your great-grandmother or others who came before. Furthermore, additional atoms and molecules from your body are released into the surrounding soil during decomposition. For every kilogram of dry body mass, approximately 32 grams of nitrogen, 10 grams of phosphorus, 4 grams of potassium, and 1 gram of magnesium are eventually contributed to the soil. Remarkably, these components act as natural fertilizers for the plants around the burial site, playing a positive role in the local ecosystem. Now, let's shift our focus to the alternative process of cremation. What happens after your body undergoes cremation? The intense heat of the cremation process leads to the conversion of most atoms in your body, hydrogen, carbon, nitrogen, oxygen, and sulfur, into gases. This transformation represents a significant change in the state of these atoms, marking another chapter in the complex journey of elements within the cosmic cycle. As we explore the aftermath of the cremation process, various gases, including water vapor, carbon dioxide, nitrogen oxides, and sulfur oxides, are released into the atmosphere. It's important to note that a significant portion of your remains, amounting to several kilograms, turns into ash during this process. Intriguingly, the weight of these ashes is roughly equivalent to your birth weight, highlighting the cyclical nature of life. Now, let's delve into the composition of these ashes. An analysis reveals that the majority of the ashes consist of phosphate and calcium. This composition makes sense, as these elements are essential to the structure of your bones, meaning these atoms primarily originate from your skeletal framework. But what happens to these ashes? They are likely to be incorporated into the soil, becoming part of the structure of plants. In turn, these plants may serve as a source of nourishment for animals and humans, essentially allowing the remnants of your existence to return to human bodies. In a fascinating twist, small fragments of you could end up in the morning cereal or burger of your great-grandchildren, enabling you to continue contributing to the sustenance of life on our planet. However, it's important to note a significant exception. Your body contains trace amounts of radioactive elements. Some of these elements undergo spontaneous fission through radioactive decay, transforming into other elements before entering the biosphere. For example, radioactive potassium may transition into calcium, while minute quantities of thorium and uranium in your body will eventually turn into lead. Alongside this decay process, some helium atoms are generated. Due to the insufficient gravitational force on our planet, helium tends to escape into space. Although a fraction of this helium may be captured by massive celestial bodies like the Sun and Jupiter, this complex interplay of elements adds a layer of complexity to the cosmic journey of atoms, highlighting the dynamic processes at play in the broader universe. As we ponder the cosmic destiny of atoms, a notable portion embarks on an extraordinary journey beyond the confines of our solar system. These atoms, once part of your body, set forth on an awe-inspiring voyage, drifting among the stars and venturing into the vastness of the cosmos. Their trajectory carries them to the farthest reaches of the universe, where they persist in perpetual motion, transcending time itself. Now, a captivating question arises: do atoms last forever? While life on Earth appears constant and predictable, marked by the rhythmic ebb and flow of tides, the daily cycle of the sun, and the unchanging progression of months, the larger cosmic panorama reveals a dynamic tapestry of changes and activities. Each day witnesses the birth and demise of millions of stars, and even our own sun, billions of years from now, is destined to face a similar fate. As our sun undergoes a transformative process, transitioning into a red giant, Earth will experience rising temperatures, ultimately leading to the extinction of life. A few billion years later, the sun will exhaust its nuclear fusion fuel, beginning its inevitable end. In this cosmic spectacle, the sun will shed its outer layers, gradually fading into darkness. The cosmic truth emerges: nothing in our universe endures eternally, or does it? Enter atoms, the elemental building blocks of matter that form the very fabric of our universe. When we contemplate the end of our individual existence, it's crucial to recognize that our bodies, composed of these enduring atoms, do not simply vanish into nothingness. Instead, they undergo a profound transformation, embarking on an intricate journey that extends beyond our mortal coil. Rather than disappearing, our bodies transform, breaking down into their fundamental components and seamlessly reintegrating into the ecosystem. In simpler terms, the atoms that once made up our bodies persist long after our physical presence has ceased. A question arises: how long can atoms endure? Is there a point at which they cease to exist? To unravel this question, we must delve into the inner workings of atoms. Atoms, as you might know, consist of protons and neutrons, surrounded by a cloud of electrons. The stability of an atom is intricately linked to the balance between the number of electrons and protons in this cloud. Ultimately, the atomic number, which determines the atom's identity, is dictated by the number of protons. For instance, helium, occupying the second position on the periodic table, has an atomic number of 2 due to its 2 protons. While the number of neutrons in an atom is typically constant, there are exceptions. In cases where an atom lacks the correct number of neutrons, it may shed a neutron, similar to misplacing a sock in the wash. This imbalance renders the atom unstable, prompting it to emit subatomic particles. Often, this emission involves the release of an electron, leading to changes within the atom. When dealing with heavy atoms, there's a likelihood that they might spontaneously break down into smaller particles, a phenomenon known as radioactive decay. This process is fundamentally random, making it challenging to predict the precise moment of breakdown or the emission of subatomic particles. Nevertheless, statistical analysis allows us to estimate the average time it takes for half of the atoms in a sample to undergo decay, termed the half-life. Since atoms possess a finite number of protons and neutrons, they generally emit particles until they reach a state where their half-life is so extensive that they essentially become stable. Take, for instance, bismuth-209, believed to have the longest decay rate, undergoing alpha decay. Its half-life is over 1 billion times longer than the current estimated age of the universe. This showcases the enduring nature of certain atoms, emphasizing that despite their dynamic nature, they can persist for unimaginably long periods. In practical terms, bismuth-209 exhibits remarkable longevity, to the point where it is often considered nearly eternal. However, the concept of true eternal life for subatomic particles raises intriguing questions about the potential decay of protons. Scientists have proposed hypotheses related to proton decay, a theoretical form of radioactive decay. One such idea, known as the GUT, Grand Unified Theory, model, suggests that protons could undergo a transformation into a positron and a neutral pion. Subsequently, this neutral pion decays into 2 gamma-ray photons. The estimated half-life for protons in this model is an astronomically extended 1.29 times 10 to the power of 34 years. This duration is exceptionally long, creating a hypothetical pathway towards eternal life for protons. However, it's important to note that as of now, there is no experimental evidence to substantiate the occurrence of proton decay. Despite the absence of conclusive experimental support, ongoing research at some of the world's leading laboratories holds the promise of potentially shedding light on this intriguing aspect of particle physics. Through a combination of luck and rigorous scientific investigation, future insights may emerge, unraveling the mysteries surrounding the potential decay of protons and offering new perspectives on the concept of eternal life at the subatomic level. From stars being born in the sky to tiny particles quietly fading away, the universe shows us a beautiful dance of creation and disappearance. Right in the middle of it all, atoms persist, changing over incredibly long periods, connecting the past, present, and future. As we think about some atoms possibly living forever and the challenging idea of true eternal life, the universe invites us to consider both the very small and the very large. Perhaps, in the dance of tiny particles, we see humanity's quest to understand life and the nature of existence. In this grand cosmic dance, our search for understanding mirrors the persistence and transformation of atoms. From ancient ideas about life to new scientific inquiries, humans continuously strive to grasp the meaning of existence and eternity. Atoms, these quiet entities that carry history within them, remind us that everything has a beginning and eventually an end. But even in this cycle of creation and dissolution, there is beauty. There is a kind of connection that ties us to the universe. The atoms in us have seen a lot, ancient times, stars, and entire galaxies. They have witnessed the universe's dance. A dance that constantly changes, an everlasting dance that transcends the limits of time and space. As we journey through the vast expanse of the universe and the tiny realm of atoms, let us appreciate the interconnectedness of all things. In the dance of tiny particles, we find parallels to our own brief existence, reminding us that, like atoms, we are part of the grand narrative of the universe that unfolds over immense spans of time.